final research project in the Optics of City of Light program. When light travels through a medium like air or a polymer, its direction and speed can change depending on the refractive index of the medium. This is the physical idea in waveguides. Using a high refractive material, you can trap and direct light in a specific direction. For this project, I used the process of mask lithography to create waveguides in the following procedure. Starting with glass or silicon substrate, you make sure you have a clean surface to work with. Then apply the monomer composite SU8-2000 with the desired depth of 2 micrometers. Spin the substrate at a high speed using centripetal force to fully cover the surface. Place the sample on top of a hot plate to evaporate excess solution at 65 and 95 degrees Celsius consecutively. Once complete, place the sample under a reflective mask with the desired structure cut into the surface. Expose the sample to a high-energy pulsing infrared laser to print the desired shape into the sample, turning the monomers into joined polymers. Repeat the baking process. Finally, develop the structure in SU8 Developer, kind of like a picture. What is left is a small set of polymer-based structures that have a higher refractive index than air. Probing this waveguide with a larger wavelength laser, I measured the power traveling through the waveguide structure as the laser scanned across, creating a graph like this, showing where more photons were able to reach the power meter by traveling through the waveguide, and not reflected off. Another important optical tool is the quantum dot. Using a lithium-based particle composite, the lab probes tiny particles that can absorb and re-emit light. Depending on how dense the composite is, you can isolate single photon emitters whose absorption scales look like this graph. An interest in optical research is to combine these two tools into one, a waveguide created by high-energy mask lithography with isolated single photon emitters found using a lower energy scanning technique. This would allow for precise control of both the emission and direction of single photons in optical applications.